Picture this. You are tasked to implement a service that needs to comply to a service level agreement where it says that the uptime of your application needs to be 100%. How would you go about that? Would you use load balancers? Would you upscale your containers so that they are able to use more memory, perhaps more CPUs? Perhaps you can even increase the physical space of your containers. How about improving your queries? If you've got SQL queries, why not think about the indexes of those queries? And your code, maybe you can identify bottlenecks in your code and improve that. There are many strategies to improve the performance of a service. However, we are talking about a very serious kind of SLA. This is where the uptime needs to be as close as possible to 100%. So close even that it is defined as 100%. How can we actually achieve this in an easy way where we don't really need to worry that much about getting our code as efficient and optimal as possible, or our queries, where we can improve the resilience and the ability to respond to requests so well that we don't need to do so much upscaling, however, still be able to upscale every time it's needed? Well, there is a way, and that's what this video is about. So stick around and let's get into it right now. In this introduction, I am mentioning a problem that is commonly found when we are working in software development. The problem is that we want to comply with the high standards of our SLAs. And for that, we try to use multiple techniques, like the ones I mentioned, and not all the time they work. And when they do work, we realize that we are using an extreme amount of resources just to comply with those standards. One solution for this is, of course, Kotlin Coroutines, which is the subject of this course. Now, the idea is that we can maximize the resource usage and get a lot of benefits by using coroutines. Now, Kotlin has implemented one version of coroutines, which we now call Kotlin Coroutines, which is kind of similar to what Java virtual threads also do these days, but they are slightly different. Kotlin Coroutines are part of a library and can only be used with a combination of a library and a plugin. So they kind of work like a DSL, but nonetheless, they work very well. But before we continue to the course, let's first understand what a thread actually is. Now, we have been using thread for years. Since the inception of Java, it's kind of one thing that we have always learned to exist in Java. Not for all programs, of course. Some programs, we don't even need to think about threads. We use threads implicitly in the main thread. But for those programs, we never even need to talk about threads, except when we are going concurrently. When we use concurrent tasks, we need to think about threads. And that's when we start using things like a scheduler, or we start using fork joins, or we start using any kind of parallel processing. And this was all made possible with the usage of threads, which had a very different evolution, which is something that I explain very candidly in this video over here, because that's where I explain also virtual threads and the difference between virtual threads and Kotlin Coroutines. But threads are heavyweight. They use a lot of resources. Threads, they share a common space, that's the heap. That's where all the objects that we create in runtime are stored. They have a register, they have a program counter, they have a stack. And threads are preemptively scheduled by our system. and they are controlled by our platform, which is our language and the JVM. So threads allow concurrent processes. And coroutines are different because they run on threads. Coroutines are not preemptively scheduled, so that means that they are not started by the system or platform, and they are not controlled by the operating system or the platform. Coroutines are cooperatively scheduled, and that means that we can start the coroutine from the code, and that the coroutine itself, only the coroutine itself, can return the control back to the thread. Coroutines run on threads. Keep that in mind. Coroutines don't stop the use of threads, but they use them in order to be able to run. And they can suspend functions. What that means is that we are running some kind of routine, which is a set of instructions which are part of the coroutine. And when our coroutine finds a blocking process, it can yield control of that thread so that another coroutine can use that thread while the blocking process is at hand. And this is interesting because it makes coroutines lightweight. Coroutines are not lightweight threads. They don't behave like a thread. A lightweight thread is, for example, a Java virtual thread. That is a lightweight thread. But coroutines are not threads. Coroutines use threads. And by the way, Java virtual threads also use threads, but the way we use them in the code make them eligible to be called lightweight threads. Not coroutines though, because the idea of cooperative scheduling is very well seen in the code. Coroutines, because of that, are not strictly limited to the amount of resources. They are more limited to the amount of threads that we have currently available to be able to run them. And probably the most amazing characteristic of a coroutine is that you can run a coroutine on a single thread, or you can, because of context switching, distribute the coroutine through multiple threads. That means that a coroutine can, if we want, start on a thread, and then for every blocking operation it finds, it may or may not use another thread to run. And you may ask now, wait a minute, if a coroutine runs on a thread, and it always occupies a thread, that means that that thread is not available while it runs. Yes, it's true. That thread is not available. Another coroutine can run on another thread, and that thread will also not be available. If a coroutine stops and yields control of the thread, then that thread becomes available again. But is that not the same as starting a thread and then stopping the thread? Because essentially we are using the same thread. We are using threads, we are stopping threads, there is no difference. So why are coroutines important anyways? Why should we use them in that circumstance, you may ask? Well, here's the thing. The key factor here is, what do coroutines do while they are blocking with the thread? For example, if I use a thread to make a REST call, just as an example, and that call takes up, let's say, so that we can visualize, it takes about 5 minutes. We are waiting 5 minutes to get the call back from the service so that we can continue from this service forward. During that time, the thread is blocked because it's waiting. Do you see now where coroutines can make a difference? Not yet? Well, imagine that this is made by a coroutine. Now the coroutine is running on this thread. The coroutine makes a call to the REST service, and now it yields control of that thread. That thread is now released, and that thread is now available to be used by other coroutines. The thread itself is always doing something. if there are enough coroutines using the system, of course. But most of the time threads are busy, and they can be very busy. And that's the whole idea. That thread that otherwise would be blocked and waiting for a cancellation from the system, or it would wait for the execution of that routine to complete and for the system to stop using that thread and make it available again for another scheduler. Now that thread can now be used for other things. It can be used for other coroutines. But to help us visualize and mentally map this in our minds, I thought about doing a sketch for you which will illustrate why coroutines can be better for us in regards to using threads. And these coroutines can be in the form of Java virtual threads or the topic of this video, Kotlin Coroutines. So let's get into it. Right over here. So first, let's draw a chart, and let's start by drawing its axis from here up until this point, and then from this point all the way up to here. This is an axis over time. So let's give it a T over here and say, just for the sake of visualizing, that this line, this axis, is being made in seconds. So let's draw now 4 lines. 1, 2, 3, and 4. And let's say that all of these lines represent threads. This will be worker thread 1, this will be worker thread 2, worker thread 3, and worker thread 4. And let's say that our coroutines are colored. And let's say that this coroutine here is colored red. Before I continue, when we launch coroutines, we need to assign them a context. Otherwise, they will have their own context. But coroutines need a context to run. This context has a lot of properties that we will see throughout this video, but one of them, which is probably the most important one, is telling the coroutines which threads are available for them to use. And so, in our example, we only have 4 threads available, and we need to pick which one is going to be assigned to this coroutine. As we have seen before, as I have mentioned before, coroutines are concurrent, so that means that this coroutine will use the first thread that becomes available. In this case, is almost random, and so it will pick up, for example, worker thread number 4, and will start running from over here. This coroutine has a task, and at some point it needs to perform a blocking operation, which would be, in this case, a GET request. When the coroutine is performing this request, because it's a blocking operation, it will release the thread to be used by other coroutines. And so, if no other thread is available, then another coroutine can pick up this thread, or it can pick another thread. And to better understand that, let me draw another coroutine using another thread. For example, this green one will use worker thread number 3, and we'll use it up until the end because it will not perform a single blocking operation. Then another one, colored blue, will use this thread all the way up until the end. And then we will have, for example, this one with a yellow color, which will use this worker thread up until the end. So these 3 do not perform any blocking operation. This one is running a GET request at this point in time, where all threads are occupied, but it releases 1. So this means that if another coroutine wants to run at this point, then, let's give it a purple color, it will be able to start running from this point onwards, and it will run from here up until, for example, this point, where 2 things can happen. Either this coroutine needs to perform a blocking operation, or it will just stop running. But it is a point where the thread gets released. This GET request probably finished off earlier. Let's say that we get a response from our service back to our client that is running on this task over here, on this red coroutine, at this point right over here. So what is happening is that the red coroutine will now try to find an available worker thread. The problem is that all of these threads are busy. Worker thread number 4 is busy with the purple coroutine, worker thread 3 is busy with the green coroutine, worker thread 2 with the blue coroutine, and worker thread 1 with the yellow coroutine. And so the red coroutine has nothing else to do but to wait for the opportunity to take control, to regain control of another thread. And that will happen at this point over here when the purple coroutine is done. And from here onwards, the red coroutine will continue to run until it finishes off its execution at this point right over here. And the reason why the red coroutine needs to get another worker thread is because at this point over here, it released the control of the coroutine that it was running on. And so here we can see that during this amount of time, from here to here, the coroutines running on worker thread 1, 2, 3, and 4, namely the yellow, blue, green, and red coroutines, they all finished at the same time. This is just a coincidence. It's just to exemplify how coroutines can work. And we actually finished 5 coroutines, including the purple one. And this was made possible because in this period from here up until here, when we were making the GET request to our service, we were waiting, and so our worker thread 4 became free. That means that the red coroutine released the control of that thread, and in that time, the purple coroutine that was waiting to start on a fresh worker thread got its opportunity at this point over here. And then it went on to perform its execution. But we saved this amount of time. And I will explain now why am I saving that we saved that amount of time. Let's look at this from the lens of running these tasks as threads, in the form of threads. So if we would start the red task from this point as a thread, up until this point where we perform the GET request to the service, nothing much different would happen between using coroutines or using just threads. They would run at the same time. Everything would happen in the same way. In fact, this would have been a reason not to use coroutines because all of the threads would run at the same time and there wouldn't be any kind of blocking request or call to another function. In this case, at this point, from this point onwards, is where we can then see the difference between both of them. So from this point up to here, now using threads, it would be completely blocked. So that means that while the thread is waiting, it becomes idle. It doesn't allow anything to run on it. It is a resource that is simply waiting and it's not doing anything. And so it is a wasteful resource, which is actually the reason why coroutines came into play and why are they so important. And then it would continue running for the amount of time that I described here from these 2 points. So let's just say almost like this would have been it. And so the full amount of time that the thread now took to run was this. And that means that the purple thread that is waiting for an opportunity to run, or let's say the purple task that is waiting to run, waiting for the thread to run, would have only been allowed to run from this point onwards. And so this is what we would see, but the purple thread would go all the way further and it would end much later. And it would end with an offset matching this time difference. This allows us to see and to make a map in our minds of how coroutines work and how threads work. And so we have seen in this basic example the simple differences between a coroutine and a thread and how when they work together they can be beneficial for us. The logic goes behind the same principle. Why would we want a thread to wait? Why would we want a thread to not do anything and be occupied with nothing, with just waiting something? Why would we wait for a response? Why would we wait for even a sleep? Why? If a thread sleeps, why should it block? Why should we keep that resource occupied with just sleeping, with just waiting? You know, when we make a thread sleep, why would we want that? Why would we want to wait 5 seconds and not release that resource? We want to wait 5 seconds, 2 seconds, 3 seconds, and we want to make requests and get a response. Sure, we want to wait for the response. But isn't that a waste of resources? So let's not do that. And if we are in that situation where we do need to deploy more tasks and to run different tasks, then perhaps that will be the time to use coroutines. But we are talking about Kotlin Coroutines in this video. And now we are having a look at basic examples in Kotlin Coroutines. And so let's start. So to get our examples running, we need, of course, a project so that we can run these examples and see how coroutines can be launched and what can we do with them. I have a project which is called E01 Kotlin Test Drives. I made this project a while ago, and it has a ton of examples. If we, for example, look for things like launch, which is something that we are going to see in a minute, we can see that there are several examples of it. If we look for things like async, there are also many examples of that. And if we look for coroutine related stuff, then we see also code that works with coroutines. But we need to understand, of course, how this all works. And for that, let's go to one module that resides over here in J.org Kotlin Coroutines. And inside of it, we will find different modules. There is one, which is the one where we are going to work in, and this is the Coroutines Crumbs Group 1. Crumbs in this sense is an analogy to breadcrumbs. So small things that we can learn from. And that means short codes, bite-sized codes, not literally, but small pieces of code where we can just learn how coroutines work. So let's go inside of it, and here we can find already a ton of different tests in the Kotlin folder, because I have here also examples that relate to interoperability between Java and Kotlin, which is also another topic that we can have a look at it later. But for now, we've got all of these examples, and they all have different situations that we can then see how Kotlin code can work with Kotlin coroutines and what are our different options. So this is a very big repository. But for now, let's create our class. I just deleted one, because I was practicing for this video. Let's create one task class. Let's call it Coroutine. Let's call it Coroutine. Yeah. Coroutine job. So we've got a coroutine job. This is our class that we are going to use for the examples of this video. What we need here, normally you wouldn't need to do this if you have one main class, but because I have many main classes distributed all over this package, the org j-singer.ktd, then I need to make different entry points. In this case, I need to create a companion object, and there I need to create my main function. All right, so this is the main function of our tests, and now we haven't done anything related to coroutines, but the first thing we need to do is to create a coroutine context, and we need a coroutine scope. There are many ways to do that, but just to give a head start, we can just say run blocking. And when we do a run blocking in the main entry point, One thing that we should do immediately is just start with unit right over here. What we have created now is actually a coroutine. It may not seem like that, but run blocking is a coroutine builder because essentially it builds coroutines, and that's the reason why it's called a coroutine builder. And now what we can do is at this point we can just call this, for example, and we can see here IntelliJ tells us immediately that this is a coroutine scope, and we can also see that this coroutine scope has a coroutine context. And if you look at the definition of run blocking, we will see that the context is defined as the context of the coroutine over here, and then here further it says that the value is an event loop of the current thread. Now the event loop, we will see that it is a blocking event loop, and that comes because of the thread that we are using to run this application. But first, now that we have a coroutine context, what we now also need is a few coroutines. But before we continue, let me show you in the chart what is really happening. So let's go to our board, and here let's draw the chart as I mentioned before. So if we go over here and do a chart like this, then we've got an axis. Again, this will be time in seconds, like this. And then over here we can get different threads. Let's say that the one we are interested in for our example is this one. This one is the thread that has the event loop. And then here we've got other coroutines, other threads. And then let's just say that because we don't know how many threads we are counting to be available, then we represent them a bit like this. And then we can say that our function will start running from this point onwards. So what happens now is that when we start our thread, it will continue to run up until this point over here, for example, where we are now starting two different coroutines. So we will try and do this. One is going to be this green one, which let's just say it will pick up the next available thread. Could be this one over here. So that means that it will start running over here. And then let's say that the other one that we launch picks up this thread over here and starts running over here. In the middle, then we are going to have a continuation of the main thread, which now runs over here. So these continue to run, all right? So what happens now is that this coroutine over here will reach a point in time where it will end, and this one will also reach the point in time where it will end. And finally, the main function will end, and then at this point we will reach the end of the running program. So that means that the total runtime should be this time over here. This will be T1. So T1 should be the same size as the longest running coroutine. So let's say, for example, if that coroutine took much longer, till here, for example, so that means that T1 would be this duration. All right, so this was our example by launching two different coroutines from a thread or a coroutine. Let's have a look at our example in our code. So we are now back to our coroutine code. We have created a class, a coroutine job, and we have already started launching one coroutine by using this run blocking. We have a coroutine scope, and we also have a context associated with it. We have also said that an event loop is responsible for that context. It's actually the context where the coroutine is running. All right, but not much different is happening here, right? We saw from our diagram, if you remember, we have one straight line where the thread is running, and that's where this coroutine now is running on. We now want to launch two different coroutines, just as in the example we saw just a few seconds ago. So let's now run those coroutines. And for that, we have different builders. The ones that are mostly used in the code are launch and async. Let's first make an example with launch. So if we create here launch a coroutine, this was just created by IntelliJ, I don't know why. But if we launch a coroutine right over here, let's just say that we will just print something. Print line starting coroutine job. That's actually a good hint from IntelliJ. Then let's give it a delay. Delay 2 seconds, like this. Let's just use idiomatic Kotlin for that. So 2 seconds, and here the delay, we still need to import it. I think I would have expected that IntelliJ would have found this quickly. Not really. So we just do it like this and it finds it. There, we have 2 seconds, and now we can print finished coroutine job. All right. And let's just launch another coroutine. Print start coroutine job. Let's give it a delay, but in this case, let's just give it a 4 seconds delay. And then afterwards, let's print it again, finished coroutine job. And to make a difference between the two, let's just say job 1 here, and then job 1 here, and then job 2 here, and then job 2. So now we've got job 1 and job 2. They are running, but before we run this program, we are interested also in knowing how long is this going to take. And for that, what I can also do is call before the run blocking a measure time in mils, the whole block, including the launch of the coroutines. And the reason why the function is not compiling now has more to do with the return type than anything else. A main function must return a void in Java or a unit in Kotlin. So this unit is correct. The only thing is that now we are measuring the time in mils, and of course we need to catch that in any case. So for that, I can just do this, which in turn makes it not necessary to use unit at all in this case. Now we've got the measure time in mils. Now we want to simply just print out this message, and for that we can just do this and print out the complete result of running all of this to a string. So, and of course this will then be logged to the console. Let's say here execution time took whatever milliseconds. If we run this code now, what would you expect to happen? Is this going to take 2, 6 seconds, 4 seconds, or it will just run immediately? So now we've got our function ready to execute. Let me just show the whole body of the function. We can see now that we will print execution time took so many milliseconds, and we measure that by calling a run blocking that will then launch the 2 different coroutines. Run blocking is a blocking coroutine. In this case, it will only use 1 thread, and this means that our graph would have a different shape, but we'll get to that at the end of this experiment. It is also important for us to log out the details of these 2 different coroutines. They are running on 1 single thread at this point, because I'm just starting run blocking with a default event loop. We will see that in the logs. What we also want to log right over here is the coroutine context. So, for example, here we can get the information about what is going on in the current coroutine that it's running. And here at the end, we can say that we want the information of the current thread. And for that, we can use thread.current thread, and this will log out the information. We can also make this more readable. We can say finished coroutine job with context, current coroutine context on thread, and then we get the information of the running thread. We can copy this into the log line for our second coroutine, and this would give us enough information so that we can take conclusions after running this. So again, would this run in no time, in 2 seconds, 4 seconds, 6 seconds, or would this just, for example, just block? So let's just run it and see what happens right there. You can see already that the code has finished running. We started out the 2 different coroutines. Then we get this right over here, finished coroutine job with context, and then finished coroutine job 2 with context. And we can see that the execution time was about 4 seconds. So we had one coroutine that takes 2 seconds and another coroutine that would take 4 seconds. In the end, the longest running coroutine is the one that determines how long this process takes to run. What's important also from these log lines is that we see the context. In both cases, we see the same blocking event loop with the same reference. And we see that it's all running on the main thread, and we see that it has assigned the number 1 for the main thread, and we've got here 5 as well. So these are log lines that tell us that both coroutines ran on the same thread, which might feel odd because we actually only just made a delay over here. And that feels odd because maybe you were thinking that this, since it is one single thread and they are delaying, so what does that mean? Doesn't that mean 6 seconds? Well, it can mean 6 seconds if we use the sleep function. And the sleep function is the traditional way of holding a thread, but this one is blocking. And now we can see if we run this code right now that it will not take 4 seconds, and instead it will take 6 seconds. So if you guessed 4 seconds on the first run and 6 seconds right now, then you are understanding how this works. So a thread will be used on both cases, and depending on using a delay or sleep, that means that we can redistribute the use of this thread for these coroutines. So let's put delay again, and let's quickly go to our board and see what actually happened here and why don't we get the same shape as we intended to, and then we'll see how do we get that shape after making a few changes in the code. So let's go to the board. So in this board, I'm going to do the same as I did in the other different charts. So I draw here an axis. This is in an axis of time. Let's put it seconds just to give it a unit. It doesn't really matter what unit it is. Here we've got a line that will be worker thread 1, the one that we are using for main. Let me just put here main. And then there are other threads in the system that are running. Right here also, and then here as well. But we are using one single thread. This is what happened in our example. So let's say that the run blocking coroutine starts running, and we'll say that this is the negligible amount of time that it runs for. And then it will, from this point onwards, run coroutine 1, which let's just say that it is the blue one, and let's say that coroutine 2 is the green one, like this. So here coroutine 1 will start. Again, this is a negligible amount of time, and then after this point we will start sleeping. So we will start the delay. Actually, you have to be careful with the terms because delay is different than sleep, although they seem to do the same thing. So from this point onwards, thread number the main thread will be used by coroutine 2, and that is this point over here. And these are all negligible times. So coroutine 1 starts from this point onwards. So let's now exaggerate and let's say that this is 2 seconds. And coroutine 2 started from here. And let's say that all of this is 4 seconds. And this is only the time. So that means that the run blocking coroutine can freely run from this point onwards. From here up until this point. And then coroutine number 1 can finish off its runtime over here. Again, a negligible amount of time. And then the run blocking coroutine will continue up until this point over here, where then coroutine 2 will resume this point over here, and then finally the run blocking coroutine can finish off and terminate the execution over here. So we've got different offsets over here of negligible runtime, and that is this one over here, which is negligible, and that's this one over here, which is also negligible, and this one over here. And that gives us a total of about 4 seconds. And this is how the first example ran, and that is how we get the 4 seconds runtime. But this is only an improvement if we compare it to how threads actually run traditionally. And for that, let's do the graph again. And again, the same graph with a time axis in seconds. And right over here, we've got the main thread. And over here, we get different other threads that are available, but we end up not using them. When we do the run blocking this way, there is only one thread. And what occurs here is that this thread will be segmented into different tasks. The first task is up to here, which is also a negligible amount of time. It will then run task 1 from here right about to here, and this will be actual 2 seconds. And then from here onwards, it will run the task number 2, which is going to be the 4 seconds. And then finally, it will continue and continue to run. And actually here in between, there's still a bit of runtime for the main task, but they are all connected to each other. And so this results in 6 seconds runtime. And this is why we can take 6 seconds on the same thread using sleep, because it literally blocks the thread. And the runtime takes only 4 seconds when we use coroutines, because they are sharing the thread with each other and they don't block the main thread. Now this is a basic principle of using the same thread, but if we go back to that same chart that we made before, we are still not there because we want to use more threads. Now, the key to that is to use coroutine contexts, and they will allow us to use different thread pools that are designated for specific context, which is something we will see on the next video. But for this video, it's important that we understand how to get there in a very easy way, regardless of what context do we choose. So let's have another look at their chart, which is this one. So in this chart, we have seen that we were using coroutines in different threads and that the main thread also had a role there. So we started out here at this point, and then here the coroutines would use different threads or the same thread. It wouldn't matter really that much. And then they would run in parallel in different threads. And then the total runtime of the application would be this one over here, up until the point where the longest running coroutine would end. So let's do just this right now, and you will be surprised if you don't know this, how fast that is, how easy it is that to change in our code. So let's go back to our IntelliJ, and over here we can now say, for example, that run blocking, instead of using the blocking event loop, which is what we saw here in the last test, it will use another coroutine context. And for example, there are different contexts in Kotlin Coroutines. We pick them up by different types. Normally for server-side development, there are 4 of them. We've got the default coroutine dispatcher, you've got the unconfined coroutine dispatcher, you've got main, and you've also got the input-output coroutine dispatcher. We can choose between all of them. They have different goals, and as I said, we are going to talk about those goals and how they work in the next video. For this video, to make something that we just saw in this chart, let's use dispatchers. Let's use exactly what IntelliJ just suggested us with AI. So we can choose dispatchers default. Just for you to know, dispatchers default is used for CPU intensive operations, so anything that is related with math is what we should use. Which doesn't necessarily mean that this is the right case to use dispatchers default. We are just using an example to understand what are contexts and how do they influence the runtime of coroutines. When I run dispatchers default now with the delay instead of sleep, we shouldn't see much of a difference in terms of runtime. But we are going to see a difference in terms of the running context and the current thread. And by the way, an important thing also to do is here inside the run blocking, the same thing at the end of the run blocking body. Here we can say finished thread or finished run blocking coroutine with context, and then we can observe also what is the difference using the run blocking coroutine in this case. So let's now run it and see what happens. As expected, the execution time was 4 seconds again, but now we've got different things. If we look at the logs, we can see that there is a default dispatcher worker 15 for run blocking. There's a default dispatcher worker 35 for job 1, and there's a default dispatcher worker 35 for coroutine 2 for job 2. And we can also see that the context is now dispatcher's default, and we can see that all of them have different references right over here, and we see that we've got 3 different coroutines. An important thing that we can see also in this case is that both of them are sharing the same thread in this case. The reason why they are sharing the same thread in this case has to do with the thread availability, because they are using the same thread here at the end. Coroutine 2 finished off later than coroutine 1. So that means that the thread that coroutine 1 was using is already freed when coroutine 2 gets back to try to use the next available thread. So it makes sense that they end up using the same thread. This is not always the case. What is true is that when the run blocking coroutine runs, it will have to use a different thread because it is running at the same time as it launches another coroutine. So that means that they forcibly need to use different threads. There are a lot to say about coroutines, about how they work and what can we do with them. But in this video, what I wanted to show you is how to use them and what are the basics for running coroutines. The basic side of coroutines, I find it many times to be not very well understood, and that's why I wanted to make this video with these charts, so that we could see and understand clearly what it means to be non-blocking and what that gives for a coroutine. It gives them an opportunity to get another thread, and that other thread, that availability, is exactly what empowers an application when it uses coroutines as a way to perform its tasks. There's a lot also to say about scheduling. What we are going to see in the next videos about this topic is we're going to talk about context, coroutine cancellation, and we are going to see also how can we work with other things in a more advanced level with other different frameworks like the Spring framework or, for example, Quarkus. Coroutines are important for reactive applications. This is something that allows these applications to be more resilient and be more fault tolerant, and also be able to support higher levels of back pressure. And they also increase the capacity of the requests that are being made to the applications. If you have any questions about these topics of this video, please make sure to fill in the comment section of this video. Make sure to read the description of the video because there's a lot of good information there. I will put also links for the different slides on Scribd that talk about these topics as well. It might help you. There are also links in the description about the repositories of with this code and also other coroutine based applications. Make sure to read that. Be sure to give us a like at the end of watching this video, and make sure to follow this channel so that you don't miss out the next coming videos about this same topic and others that will come up. And until the next video, stay tech, keep programming, be kind, and have a good one. As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.